This lecture is kind of extension of the previous one. So whatever we have seen so far about convex optimization, here we will see that most of those algorithms with some minor modifications, they can be applied in non-convex regime as well. But then the important thing about this lecture is to see how we can apply them in non-convex regimes. Well, even more importantly, what are the main problems that will appear in non-convex optimization? And why is it really important? Because whenever you see a machine learning problem, in most scenarios at least, you will see some form of non-convexity somewhere. Okay, so some learning outcomes of this lecture. So then it's going to be a recap of whatever we have seen so far in lecture 2 and 3, essentially. Then the hardness of non-convex problem, what are the main hardness? And then you will see that some very innocent looking problems, they can be extremely hard actually. So really you cannot judge based on just the face of the problem. Finding stationary points for non-convex optimization. First, what is a stationary point? So far we have seen convexity, optimality, optimal points, but now from now on we will only talk about critical points or stationary points. What is their definition and how we can find them? Then we see the definitions of saddle points, which are pretty important in non-convex landscape, and then how we can escape them. Well, the even broader question is if we can escape them or not. Then how we can find here stationary points, but then we can extend that to find an approximate local minima or not. And then finally some convergence results in the face of large-scale non-convex optimization. Okay, so let's dive in first to some definitions of non-convex optimization. So some basics first. Let's start with our famous problem of minimizing empirical risk plus some regularizer. For most part of this lecture, we don't need regularizer, but you know how to handle that for different cases of regularizer. If it is convex, strongly convex, non-convex, non-smooth, you know how to deal with that. So far in lecture 2 and 3, we have discussed about existence of one globally optimal solution. And there are many different solvers that you can use depending on the structure of the problem and depending on the available information that you have on computational complexity. So for instance, if you do have access to the second order gradients, to the Hessian, then you can just run Newton methods or some versions of that. Okay, in the deterministic setup, which was lecture 2, we have seen there is something called gradient oracle, which is essentially a machine that takes as an input. So again, we are talking about minimizing 1 over n summation of fi, so a finite sum. So gradient oracle takes one index of that f of I, so one index I, and then x, and then gives to you f of I of x, so the function evaluated at that point and that index, and the gradient of that. So this is called simple gradient oracle, and a very good measure to see how complex solving an optimization problem is. We have seen, and then in the deterministic setup, the gradient oracle load is usually linear with n, essentially because we need all the gradients to be able to run one gradient descent iteration. And we have n gradients, so it's linear with n. Then we have seen gradient family for smooth problems, and if we do have non-smooth problem, could be due to regularizer or whatever, then we can use subgradients or proximal methods, okay? Composite function is essentially f plus h, where f is very nice, has some very nice property, but then g doesn't have those nice property. For instance, it's non-smooth. Then in the next lecture, lecture 3, we have seen that how we can handle stochastic solutions where the gradient oracle load would be independent of n in the vanilla version of SGD. So a stochastic gradient descent family for a smooth problem, again for non-smooth problem, how we can handle them. And then we have seen the importance of noise reduction techniques, usually adaptive mini batch sizes, SVRG, Saga, and all those kind of things. Okay, but now let's dive into non-convex optimization. So those were just for convex optimization. For non-convex optimization, a lot of strange things happens actually. So first, why is it important to go with non-convex optimization? Because usually I can say that almost all the problems that you can imagine, they can be somehow formulated as some form of non-convex optimization. So if you have a solver for that, then that's great, because then you can solve most of the problem that you may face in your life. But what is bad about that? So we know that we don't have solution for everything. So it essentially means that probably there is something wrong with these non-convex optimization, or at least these formulations. So first of all, in these formulation, we will see later on more formally, but local optimality may not mean global optimality. That was great thing about convex optimization, because there we could have that very, very nice rule of linear upper bound given by convexity, which says that f of x minus f of y is greater than a linear function. So gradient of f evaluated at x and y minus x, for instance. Well, let's say y minus x, and then here we have x and y minus x. Here we need a transpose. But then what it says that in that function that you will see on top, here, if we know that the whole function will be lower bounded by this. So if we know that this is one point, which is called local optimal, then it means that it should be globally optimal. So this is just by definition of convexity. We don't have that definition here in non-convex scenario. So if this is a non-convex shape, and then we might end up to this point. For this part, we can say that this is a locally convex function, and then we do have this property, and then we can say by that property that this point is a local minima, but then that's all. We cannot really say that this is globally optimal. So that is very problematic. But then, and then you can see the importance of initialization. So again, in this figure, if we run some simple first order methods, then we can find this point. Just assume that we can do that. So run gradient descent here, go downhill, and then find this part. But then if you're just lucky that start from this point or start from that point and then go downhill, then you can find the real local minima, the real global minima here. So it's really, really important how to initialize. But this curve, this non-convex landscape, is actually a pretty nice one. What would happen if you have a function like that? A lot of local minima here. Definitely here, of course, the choice of initializations and initial point is really important here, but you need to do something more here. You need to smooth that figure somehow, right? So this is proper initialization. Another things, which is, I guess, one of the hardest things that you will see in non-convex is this one, actually. So we had a very nice rule of the first order optimality. It says that whenever gradient vanishes, we are at the local minima, and then by convexity, this is globally minima. So this is called first order optimality criteria. We have seen that in lecture 2. So that's essentially necessary and sufficient condition. So that's why that we only work with first order gradient. That's just fine. We will go to the second orders and all those things, acceleration methods, blah, 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 only because we want faster convergence. It's not because we want convergence. But here, it's just necessary condition. You will see in 2 or 3 slides from now that you can have lots of points where the gradient vanishes, but the point is neither local minima nor local max. First of all, we cannot say anything about global position of that point, if it is globally optimal point or not. But even more than that, we cannot even say that if it is local minima or not. So one very simple example in 2 dimensions is like this curve, where the gradient is actually 0 here. So you will run a gradient descent, and then you will converge to this point where the gradient vanishes, and that's it. So gradient descent solver says that this is the local. I have converged to 0 with any criteria of quitting that iteration. Then you will say that, okay, now I converge, so this is my local minima, and clearly this is not local minima. This is called saddle point. And we will see a lot of that in non-convex landscape. So then we can say only necessary conditions. So what does it mean? It means that a point is local minima if, well, let's say all the local minimas, they should have vanishing gradient. But all the points that have vanishing gradient, they are not necessarily local minima or local maxima. So that's the meaning of this necessary condition here. So we're going to lose this sufficient condition, which is pretty important here. Okay, so let's just start with this very, to me at least, very innocent looking problem. This is, you can see this, and then W is a binary vector of dimension n, and the whole idea, this is called subset sum problem. The whole idea is just to find a subset of those vectors a1 to an. So those are some integers, for example. And the whole idea is just to find the subset of m that sums to b, okay? You can write down as an optimization problem like this, so that's great because, as I said, most of the problem can be somehow formulated as a non-convex problem. This is non-convex due to the second term, W transpose minus W. And then we have something in the first term. So this is in general something like x to power 2 minus y to power 2. So this is kind of non-convex. But then, can we achieve the global optimal point? Clearly, you can see from that the globally optimal solution is just 0. So if there is any in the best solution, if there is such a solution that sums up to b, then the first term gonna vanish, and then the second term will vanish as well. So you will end up to solution 0. But can you achieve that? You can, of course, try, and there is, I guess, that $1 million for solving these kind of problems if you can show that p is in MP. But at least so far, there is no efficient solvers that finds to the globally optimal solution. So okay, so let's give up finding the optimal solution. Can we run gradient descent to find the local solution for this? Local solution again means the point that gradient vanishes. We have seen that if the surface is like this, then definitely we cannot find globally. We may not, let's say, we may not be able to find the locally optimal solution, even that. Okay, so what we can say? So we cannot say that we can find globally optimal solution. We cannot say that even we can find locally optimal solutions. Then why on earth we should just talk about non-convex optimization? And just by, you know that there is a well-known theorem called curse of dimensionality. And in the main version, it says that the number of these saddle points will be exponentially more than the number of local minima. So if you just randomly initialize from some points, then the chance of getting stuck in some saddle points would be much, much more, overwhelmingly more than the chance of getting stuck to some local minima. And then that chance will increase and increase and increase as you increase the dimension of the problem. So if you just say that I want to train a deep neural network with 1 million parameters or 2 million parameters, then the number of saddle points is way more than the number of local minima. But how we can even solve that problem or find some locally optimal solution? So all these things is not to discourage, it's just to say that whatever the results that we have, whatever convergence analysis that we can have, they might not be as strong as the convex case, okay? At least so far. It doesn't mean that we don't have any result. We will see a lot of results here in this lecture anyway. So just be aware of this, okay? Okay, so something more now, more formal about non-convex optimization. Definition 1 is like a stationary point or critical point. This is the set of all points at which gradient vanishes. So that's a basic definition. In the convex land, a stationary point is globally minima of that. Well, it doesn't have to be minima, it could be maxima as well, but then there is just one globally optimal solution for that. Local minima is a critical point, so a point at which gradient vanishes, and we do have this, Hessian positive definite. Well, you can have Hessian positive semi-definite as well, so you can allow eigenvalues 0 as well. And that could be, again, local minima. I'm just saying could be because there are some saddle points that satisfy that condition. So if you say that the Hessian is positive semi-definite, it doesn't mean necessarily that you are having a local minima. It should be positive definite. What is the meaning of that? We're going to need that later on, but I can just write it down. So if you write down the second, what is the definition of positive definiteness? It means that for any vector v, V transpose the Hessian that we do have at point W, V for any non-zero V, for all V then this guy should be positive. Okay? So this is the meaning of PD. And why is it important? Because it just says that, let's just write down the second order Taylor series of f w plus some v. Pick some vector v. Why vector? Because w is parameters that you want to optimize, so there are lots of parameters, and then just go to some other random direction. Let's say that w just wants some random direction. This guy is approximately equal to f of w plus gradient of f at w transpose v plus v transpose, oh, half of that guy, v transpose Hessian of f at wk v. So if we say that this condition satisfies, then it means that this term is positive, right? Then it essentially means that f at w plus v should be larger than f at w. So it essentially means that the curvatures in all directions v, whatever direction is that, and that holds for all v. So for all direction, it just doesn't matter in which direction you go, you're going to improve the function, right? So you're going to increase the function. So that's the meaning of having a local minima here. And then you can see that from this, the first curve on left, which is x2 plus y2. So if you are at local minima, it just doesn't matter in which direction you're going to go. You're going to improve the function, okay? So that's the meaning of this positive definiteness here. Of course, similarly, you can define local maxima at the critical point where this gradient vanishes. So here, this term going to be negative, and then f of w and v for all vectors v going to be smaller than f of w. So that's the local maxima. But what would happen if this guy here is neither PD, well, it's not PSD essentially? Then what would happen? So it has some both positive and negative eigenvalues. Then depending on which v you choose, positive and negative eigenvalue means that there are some v for which this guy is going to be positive. There are some other v's for which this will be negative, corresponding to the positive eigenvalue or the negative eigenvalue. Well, the eigenvectors corresponding to those eigenvalues. So it means that if you choose to go towards some directions, you can improve this guy. So this guy is going to be larger than that. And if you choose to go to some other directions, then this guy is going to be smaller than that. So it really depends on which direction you choose. And that is actually what happens in the second curve, where this is x to power 2 minus y to power 2. So here you can see that, well, let's see. This is z x to power 2 minus y to power 2. So for a constant y, the gradient of z with respect to x, so for constant y, this is 2x, right? And the gradient of z with respect to y, this is minus 2y. So what does it mean? And then you can take the second derivative. So if you fix this guy, then it means that with respect to x, we have curves like that, right? So we do have local minima. The point at which gradient vanishes with respect to x corresponds to local minima. So gradient of x0 means minima. Well, we can only say that there's local minima. And if you fix this guy, then z is like some constant minus y to power 2. So then in that case, it's something like that. And then the gradient of y vanishes. It means that we have some local maxima. Right? Now I'm giving you a vanishing point, gradient of x0 and gradient of y0. What you can say at this point? So it's a crossing point where you have a curve like that with respect to x, and you have a curve like that with respect to y. So it's both local minima with respect to some coordinates and local maxima with respect to some other coordinates. And that's what happens here. So you can see that with respect to these coordinates is local minima, and then here is local maxima. So this is called non-degenerate saddle points. And this is almost the easiest class of saddle points that we know how to handle them. But it's not only the only class of saddle points. There are lots of other classes of saddle points that for some of them, really, we don't have any idea how we can address them. But you can easily see that it might be that here, what would happen if I give you the second order information? What does it mean? It means that I give the Hessian at this point. Can you escape this saddle point or not? You just need to go downhill, right? Because there is no point of going to this direction. Essentially, what we do need is just to iterate and then go somewhere, right? So this is the whole idea of iterative algorithm. Start from some point, go somewhere. And then that somewhere should be somehow intelligently chosen for some convergence, right? If I tell you that I'm here, and for this specific function, I'm just giving you both eigenvalues here. So essentially eigenvectors. I'm just telling you that there is an eigenvector here that if you move toward that direction, the function gonna increase. And there is another eigenvector here that if you move toward that direction, the function gonna decrease. So a natural choice is go downhill, right? So then you can just go downhill and then run your gradient descent. Then you don't need any Hessian information anymore, right? So this is the basic of Hessian-based escaping from saddle point, a very simple one. What's the problem? You need Hessian information to run that. We will see that. Okay, cool. So in convex lang, as we have said, let's consider this function a finite sum, and then we have in convex land, what we call optimality gap is the gap between your gradient, the norm of your gradient, and 0. This is called optimality gap. So once you close this gap, then you are reaching the optimal point. In nonconvexity, the only thing that we can say is that whenever gradient vanishes, we are at a stationary point or critical point, and that stationary point could be local minima, local maxima, or saddle point. So that's why it's just called a stationarity gap. Then the so-called second order necessary point. Why second order? Because it used second order information Hessian. And why necessary? Because we need to have this condition. This is just necessary condition for local minima. There are some saddle points that satisfy these second order necessary conditions, but then they are just saddle points. They are not local minima. That's why it's called second order necessary point. But then that's fine. That's okay, we can use them. So it essentially says that the gradient first order should vanish and second order should be PSD matrix. So it's not PD matrix, that's why that there are some saddle points there. But that's okay, because if a matrix is like this, so if a Hessian is PD, then it means that we are not in non-degenerate saddle point anymore, because in order to be here, we need to have some negative eigenvalue. Whereas by this definition, we don't have any negative eigenvalue, okay? So this is the great thing. So if we can ensure that, then we can say that, okay, at least we don't have no non-degenerate saddle point. And then, of course, we can define an approximate second order point, second order necessary point, which is define just a ball around, or a tolerance around this gradient being 0, and then your Hessian being positive semi-definite, just define some ball and then say how fast you can converge to that ball. It's just a tool for mathematical analysis. So approximate second order point and then see how fast you can converge to that ball. And then there are lots of complexity measures here. It's a little bit more richer, the number of these measures, than convex analysis, which is mainly based on the number of iterates. Here, there are lots of things. So first is the number of calls to the gradient oracle. So the number of gradient evaluations, as we have seen. So you will just give a point and an index, and that gradient oracle will tell you the function and gradient at that index, at that point. And the number of times that we need to call this gradient oracle, this is called complexity or gradient evaluation. And then, of course, there are lots of other things, like the number of times that we need Hessian vector products, especially for second order algorithms, the number of times that we need to alternate between different subproblems. You will see that in coordinate descent, for instance. So there are lots of other measures as well. But then this is the most prevalent one that people are using. And we will use that as well. Okay. We need 3 main assumptions here, and on top of that, we may need some time to have some form of convexity. If we do need, then you know the definitions. Here, actually, we need just one more definition. So let me go through them, or one more assumption. The first assumption here says that f should be bounded below, which is quite okay, at least in machine learning. Why? Because most of the objectives are like loss functions or penalties, and then they are for free lower bounded by 0. Okay, so that's for free f-inf 0 for at least machine learning applications. But then we do need that. Then usually we do have, for a smoothness, we do have gradient Lipschitz continuous. We have seen that so far. So the gradients should not change. If we change a little bit the parameters, then the gradients would not change so much. So there is a bound defined by this LG, which is called LG smooth function, or LG gradient Lipschitz continuous. But then on top of that, since in some of algorithms, we're gonna need to work on curvature information, which is the second order informations, or the Hessian, then we need a bound on that as well. Because if, just imagine that in this curve here, the second order, well, the curvature changed a lot, then you cannot have so much guarantee on that. So you need to have some form of regularity or smoothness on that as well. So it means this. So exactly the same thing with a different coefficient here. And then you can just apply this definition, so the gradient and Hessian Lipschitz definitions to the Taylor theories, and then say that we have seen that quadratic upper bound so far, which is from a smoothness. But then we can have from this Hessian Lipschitz continuity, then we have now a cubic upper bound as well. And we're going to use this cubic upper bound later on sometime. So that's it, essentially. So we're going to have a new upper bound as well. OK, cool. Any questions so far? OK, great. So in what follows, we will have 3 different sections. OK, in the first one, we will see how we can find a stationary point. Those stationary point doesn't have to be necessarily a local minima. OK, we are OK to find just a stationary point. And we want to see how hard it is to find a stationary point. And in some problems, can we say that stationary point under some conditions can be even local minima, or even can it be a globally optimal solution, global minima or not, under which structure on the problem, non-convex problem, we can say that. Okay, so pretty strong conditions, or a statement, so as to say. Then in the next part, we will see, okay, there are some problems with the first things, as you can imagine. We cannot apply that for all problems. But then we will see, is there any solver that can solve or at least address somehow some generic non-convex problems or not, where we don't have those desirable structures. Again, everything is about stationary points, so not local minima, and then we're going to extend everything to finding local minima under generic assumptions. Okay, cool. So let's go to the first one. So the first one, it says that try to reformulate your problem, and this is pretty much all we can say about that. So it says that for some problems, they may seem non-convex, but then there could be some form of formulations that you can use to make it convex. Or, for example, in the case of minimum eigenvalue, it's a non-convex in Euclidean space, but then you can just change the space, go to the Riemannian manifold, and then that's going to be a convex there, and then you can define an optimization. A very easy Newton solver that can solve that to the optimality. But then not in the Euclidean space. Euclidean space is just defined by this norm here. So what I'm saying is that this is a solution here for this specific type of problems, which is pretty important type of problems. But you cannot apply that everywhere. And you really need to be creative, really have some insight about your specific problem. So you may be able to apply something like that. You have seen a lot of other kind of problems where they are non-convex, but then you can run some solver and then find a globally optimal solution. Okay. Another kind of problems, it's invex problem. We will see that later on, the definitions somehow. But then quasi-convex problem. So you have seen that they are not convex. They are definitely non-convex, but then the function is like, so we don't have this. So the function is like this. Okay, definitely is non-convex, but then can you solve it to the global optimal solution? Yes, you're sure you can do that. How you can do that? Or even a function like that, where gradient vanishes. You cannot run gradient, but then you can run bisection search method, right? You have seen that in lecture 2. This is not convex, but this is called quasi-convex. And then you can find there is just one globally optimal solution. You can find that very efficiently, very easily at the same order of gradient descent. So you will not lose anything. But then the thing is that you should show that, first you should show that your specific problem satisfies those conditions, if you're lucky enough. And definitely not a general solver anyway. So usually ad hoc, no generic approach, problem specific, but if you're happy, then that's great. Go for that. But okay, let's see if we can use gradient descent. What would happen? What I'm gonna do, assume, is that in convexity, we have this for all wk, we have this inequality here, okay? But what would happen, just imagine that instead of having, so this should hold for all points, but then we do have that for just one specific point. Let's call that w star. It doesn't have to be the optimal solution, okay? But just assume that around w star, for now, let's assume that this is the optimal solution that we look for. But then the function is not convex. The function satisfies this constraint, this inequality, only around that point. So let's call it one-point convexity, okay? And then, by the way, you can show from the second order approximation of Taylor that most of the functions will satisfy that around their local minima anyway. Then in that case, can we run gradient descent and find some stationary point? So you see the condition. The condition is that I do have some structure on the problem, and the structure is not as strong as convexity, so we don't have this inequality everywhere, but then we do have this inequality with respect to w star. Okay, only that point. But then we do have this structure. For your specific problem, for instance, in any application, you should show that you do have that with respect to w star. Okay? But assume that we do have that here. Can we run simple gradient descent and converge? And the answer is actually yes. So the updates that we do have is like this: wk plus 1 equal to wk minus 1 over step size, which is 1 over lg. lg was the smoothness of the function, gradient of f around wk. So this is the updates that we have. And with that update, and the only assumptions that we have is that the function, of course, by definition, is lg smooth, right? So lg smoothness means that f of v is smaller than f of w. Let's see. Let's make it even easier. F of w plus v, for every v, is smaller than f of w plus gradient of f at w transpose v plus lg half v transpose gradient Hessian of fw v. Okay? Well, we don't need that anymore, and then that's gonna be v2. That's norm. We'll assume that all the norms are norm 2. Okay, so this is the definition of smoothness. Use this definition and just plug in wk plus 1 for v plus w. Okay? If you plug it in, then from that you will see that we do have the first term. I just plug it in, and you can have this. Okay? And you have the same terms here. Then that's going to be simplified to something like that. Then just define delta k as the distance between f of wk and f star, which is defined as f evaluated at w star. And just remember that we don't have definition of convexity everywhere, but we do have definition of convexity only with respect to w star. So we do have that. Then what I'm going to do is that, so this is again what we call one-point convexity around that w star. That's it only. So just consider this equation here, okay? And from this equation, just add and subtract f star. Then you can have this. So it's gonna be delta k plus 1, which is essentially the left-hand side of this guy, f of wk minus f star. Smaller than f of wk goes to the right-hand side minus f star, so it's going to be delta k minus this guy, okay? And then you can somehow bound this guy using Cauchy-Schwarz inequality by saying that delta k, we have that because this is definition of one-point convexity. And then you can just show, just follow these steps, and then easily see that delta k will reduce at every iteration, and at iteration k, delta k will be of the order of 1 over lk. Actually, that should be lg over lk, and there are some other constants as well, but the constant in the denominator are going to be lg. So what does it mean? It means that if we want delta k, which is the difference from your point, so this is the definition of delta k. If you want to be close enough to this guy with distance epsilon, then k, the number of iterations that you need to have, should be of the order of Lg divided by that epsilon g, your desire. So what does it mean? It means that for the convergence, and actually you can see that for strong convexity, you can see that. So I'm just turning it on again. But then you can see the same proof. So if you look at the proof of strong convexity assumptions with the smoothness, for instance, without the strong convexity with the smoothness and everything, then you will see that usually the only thing that we need is to have this one-point convexity, is to have f of wk minus f star being smaller than this. So we don't need that for any point, any other point. We only need that for that specific point. What we have just shown is that if we do have only this, so 1 point, then we can run gradient descent. And this is our definition of 1-point convexity. In every call, we're going to need to compute the gradient. So we need to have order of n gradient oracles per call, per iteration, that many calls per iteration. And then the number of iterations, as we have shown, is in the order of Lg by epsilon. So the number of, for Lg smooth functions, that's satisfying this 1-point convexity. And at the end of the day, we're going to need of the order of n Lg divided by epsilon to actually converge to that W star. So for any point of the function where we do satisfy this condition for any point like W star, then we can converge to that point. But what would happen if that W is globally optimal solution? Then that's it. We can converge to the global optimal solution. But you need to be able to show that there exists a globally optimal solution, which is quite OK. We can usually show that in our functions. But then you need to be able to show that for that globally optimal solution, W star, and for all other Wk, you're going to satisfy this inequality. And if so, then you can converge to that. So there is a structure here hidden that you need to be able to show that. And if you can do that, then you can run gradient descent and you can converge. OK, so one example where this guy holds is like this function here. And then you can show that for a function of this form. Let me make it a little bit. So these are non-convex, but then we can show that we can have something like that. And then we can converge, actually, by running gradient descent. OK, but why not using that for non-convex? First of all, we're going to need this structure. And for most problems, it might not be that much easy to show this structure first. Second, we have very poor scalability with n. And this is not something good, because if you want to run that for a very big data set, then n really explodes, and then you cannot run that. And again, we are optimizing a finite sum over n fi. Okay, that is n. And at the end of the day, we can only say that we converge to a stationary point. We can converge to W star. That's it. That's the only thing that we can say. But what is W star? Nobody knows. So that was a good example in the sense that it shows that you really don't need convexity for all points to be able to converge and use traditional gradient descent, whatever we have learned so far in lecture 1, 2, and 3. So here we are in the convex land in the left, where we do have convexity definition, mu strong convexity, this definition, these two definitions, and then mu strong convex and Lg smooth, where we can have this inequality. And then we know that in all these conditions, we can have convergence depending on which algorithm we can run. We can have some sort of convergence to something with some iterations, OK? What would happen, just hypothetically, what would happen if instead of having this for all v, we did that, so the first one, convex f, we did that in the right-hand side only for W star, for some beta. We have seen that, right? We see that in that case, we can really converge with exactly the same order as we can converge here. So the order is exactly the same. We are not doing anything and we are not losing anything. So we just run gradient descent with exactly the same order. Here we converge to the optimal solution. Here we can converge the same order, at least theoretically. Now, what if the function is not mu strongly convex? So we don't have this inequality. Well, this is pretty general. You can put any v instead of W star, OK? But then what would happen if we do have that only for W star for some constant beta, which doesn't have to be mu, but for some positive constant beta? What would happen if we do have that? And so what I'm trying to do is just making similar form of constraints or inequalities that those inequalities, we can have them, but the function doesn't need to be convex. So they are much more general than convex functions or mu strong convex functions. So there are lots of functions which are not convex or mu strongly convex, but then they can satisfy these conditions, okay? And then similar to this inequality, what would happen if we have something like that? This is actually a pretty important inequality. You have shown that, I guess, in your homework 1. And in proof of homework 2, most of the proofs are actually based on this. So you can see that although we are assuming that the function is mu strongly convex, but in all the steps of, the first thing that we will show is that if the function is mu strongly convex, then we do have this inequality, okay, which is called PL inequality. And once we do prove that this inequality holds, then everything follows from this inequality. So really, we didn't need to have mu strong convexity, and this inequality is much more general than mu strong convexity. So there are lots of functions called invex functions that, so not convex, invex function, that they satisfy PL inequality, but they are not actually mu strongly convex. So one of such functions is, let me see. So one of such functions is like this. Let me just erase everything here. So this function definitely is not convex. 2 points here, and then it's not beyond. The function is not below this guy, so definitely not convex, so not strongly convex. But then there's invex function that satisfy this PL inequality. What does it mean, PL inequality? Well, it essentially says that whenever we go further and further from the optimal point, okay, like here, this is the optimal point, but as we move on, okay, the gradients should grow larger than a linear function. So this is the meaning of that. We don't need the convexity definition. So it just says that there should be some lower bound, a linear function, on the gradients, improvements, okay? This is the meaning of this inequality. But then here we have an invex function, not a strongly convex function, even not convex function, but then we can really run the iterations of gradient descent with a strong convexity assumption. The proof would be exactly the same. So what does it mean? It means that whatever convergence we do have for this strong convexity, if it just happens that we do have this inequality somewhere, then that's it. So we do have the same convergence rate. So linear convergence rate is so-called. And then essentially you can now define something for this one as well. So again, if it just happens for your specific problem, that there is a structure like this, you can show that, then you can converge to that W star in a linear time. And these are just some references that's showing that for their specific problems, at least, those inequalities hold, actually. So for two-layer neural network, for instance, under some conditions, I guess that here you should have ReLU activations and some other conditions on the data, then you can show that this would satisfy. And that's it, okay? But what about convergence rate? We have already said and then showed for the first one that we do have exactly the same convergence rate because all the steps of the proof would be exactly the same, and then all the development of the algorithm would be the same. So the hardness of the problem is just to show that these inequalities hold for you, and then you can just use the rest would be extremely easy. So same proof, same algorithm, same convergence proof, everything is the same. So for instance, gradient descent or stochastic gradient descent converges with O of epsilon 2 here. So it means that convergence in order of O of 1 over a square root of k, something like that. Then in that case, the same thing exactly happens. If the function happens to be a smooth, we do have this convergence here, same convergence here, sublinear convergence. If on top of that we have strong convexity, we have seen that we do have linear convergence. Exactly the same thing, we do have linear convergence here. Same algorithm as well. Gradient descent here with the smooth functions, gradient descent there with the smooth functions, same convergence rate, and then the same thing happens for the last one. Okay, so nothing more to say. Just to sum up, there are some functions for which either we can show that this specific function after some reformulations is like a strong function, a strongly convex function or whatever. And for those functions, we are done because then we can use convex solvers. For some other functions, it might be that we can show there are some some weaker inequality holds, and for the case of one-point convexity, the function doesn't have to be convex everywhere, but it should be convex around W star. And if so, then that's it. We can again solve those problems. May not be to the optimality, because that W star doesn't have to be the optimal point, but then W star is just some point, and then we can converge very fast to that point. So just to make it clear, these inequalities that I have mentioned for, let's say, one-point convexity, they doesn't have to be valid for all the support of the function. The thing is that you need to be able to show that for some region of interest, you have that with respect to some W star that you are happy with, okay? So whatever W star is, you're going to converge to that, okay? And the whole idea here is that, for example, assume this function, and you may not be able to show that one-point convexity neither with respect to this nor with respect to that. But just assume that this is your W star, and somehow magically you know that for all the points, magically means that you have shown that, for all the points within that set, for all W's that coming from here, you have that one-point convexity. So it means that still you're going to need to have proper initializations, but then it's not as hard as just running gradient descent without knowing what you should do, right? It's just to show that that inequality holds for all W that belongs to that set. So wherever you pick W here, and then you can just run gradient descent, and then you can converge with exactly the same rate as the normal gradient descent running on a convex function everywhere, okay? So this is the whole idea here that these papers have shown actually. So they have shown that there are some region for which we can converge, but then we need a proper initialization as well to make sure that our first guess, and of course all the guess onward, they all be within this set.